Good day, everyone. I'm Fedor Duzhin, and I'm going to be your main course instructor in ordinary differential equations. So note that our course is flipped classroom, which means all our lectures are going to be online. Well, I hope you're going to enjoy these lectures because, well, although everything is online, still I can write equations here. So whenever I need to teach a word example, I'm going to be able to do it. Then, if you have questions, if you don't understand anything in the course material, please post your questions on our online forum. Well, and finally, to give you a little bit of interactivity, you know, in class sometimes you have these clickers or little built-in quizzes. So now we are going to do it too, but only online. So this lecture is supplemented with a series of mini quizzes for you to understand the material better. Well, so here is the plan for today's lecture. So please note that this is going to be part 1, this is going to be part 2, this is going to be part 3, this is going to be part 4, this is going to be part 5, part 6, part 7, part 8, part 9. And then note that there's going to be some little quizzes. There's going to be a little quiz here, a little quiz here, a little quiz here, and a little quiz here for you to understand the material better. Well, here is our textbook. It is on the course page, so you can just download it for free. Well, then before each lecture, I'm going to tell you what kind of material you need to review in order to understand the lecture. So now we have our first lecture. And in order to understand it, you need to review a few concepts from previous courses. And I'm serious about it. So if you have forgotten what a vector field is, then stop the lecture and review this material, please. All right, so I hope it is clear. So now I'm going to continue with a few warnings about the theory of differential equations. Well, here is sort of a motivating example. So this example is not related to the theory of differential equations, but it is a good analogy. Well, I hope it is something familiar to you, right? So this is a very, very important function in mathematics, and I attached the graph of this function. What is important about it is that it is impossible to express this function as a single equation involving, well, nothing else but familiar functions like logarithm, exponential, and trigonometric functions, powers, I don't know, and arithmetic operations. And so in order to express this function, one essentially has to use an integral, and there is no other way. But even though it is impossible to express it as a simple formula, it is still possible to work with it. This is probably the most important function in probability and statistics, very widely used in applications of mathematics, and this fact does not prevent us from, well, say, graphing it, studying its properties, computing it with any required precision, and so on and so forth. Well, and there are a glimpse to the properties of the cumulative distribution function of the standard normal distribution, well, can be done by, well, simply differentiating it, right? So since our function is expressed as the integral, we can apply the fundamental theorem of calculus to differentiate it, right? So I hope you still remember that if you have an integral from a to x of some function, say f of t dt, and then if you differentiate this with respect to x, so with respect to the upper limit of integration, then you just get the integrand, but only at x instead of t. Right, so applying this, we can find the first derivative of phi and the second derivative of phi, and then we can derive some of its properties. So here is an analogy, right? So if you know that a certain function satisfies this differential equation, well, we don't know what it is, what the differential equation is, but suppose that I'm just telling you that, okay, so let y be such that y prime equals y squared plus cosine square x plus 1, right? So here y is a function of x. Well, then know that the right hand side here, y square is non-negative, right? Because it is the square. Cosine square is again, it's the square is non-negative. And 1 is strictly positive, so the right hand side is strictly positive, so the derivative is strictly positive, and hence this function y is strictly increasing. Right? Its derivative is not only positive, but it is bigger than or equal to 0. So although we can't really find the function y, but what we do know is that it has to be increasing. Right? So the theory of differential equations is sort of is built on observations like this. Right? So, and it is important to know that if I just give you some differential equation, like if I just ask you to write that y prime equals, I don't know, y squared minus x squared plus 1 over y plus x plus logarithm x plus 1. Well, any expression that relates the unknown function and its derivative, then chances are that it is impossible to solve it explicitly. And the theory of differential equations is mostly about being able to derive properties of solutions without solving the differential equation explicitly. Well, but it hasn't been like this forever, right? So previously mathematicians invented a lot of specific ways to solve very small classes of differential equations, but of course, no matter how long you try to study these specific ways of solving some classes, particular classes of differential equations, you are not going to be you're not going to best the computer in it. So it doesn't really make sense to try to learn all these ways to solve particular differential equations. Well, unless of course you just like it, unless you're a big class. So so in our class we are going to only solve a few. So we are going to see a few most important methods to solve some particular differential equations. So, and on purpose I did not include some methods that are usually included into a class in ordinary differential equations, because I don't want you to get bored with just a lot of the specific methods, and I kind of killed it in favor of general theory of differential equations, right? So in our course we are going to concentrate on sort of ways to derive properties of differential equations, or to model real life problems with differential equations with